And so that's where the Shannon Nyquist Sampling Theorem comes into play. The Shannon Nyquist Sampling Theorem is really simple and straightforward. It simply just states something along the lines of, to be able to measure the maximum frequency in a signal or in a data set, the sampling frequency of the signal must be 2 times or more than 2 times that maximum frequency. So in other words, if your maximum frequency you expect is 10 hertz, or you expect something to happen 10 times per second, you need to sample at more than 20 times per second. And so this is the simplicity of the Shannon Nyquist Sampling Theorem. But putting it into practice is not always the most straightforward. Okay, so we're going to consider the simplest theoretical case right here. And to do this, I've generated a 100 hertz perfect sine wave, or at least a simulation of a 100 hertz perfect sine wave that you can see on the chart on the left here in blue or aqua or whatever kind of color you want to call it. But then we are sampling that 1 second 100 hertz sine wave in red here. And you can see initially we are sampling it at 50 hertz. But we know from this generated signal that the only thing in it, since it's a perfect sine wave, is a 100 hertz frequency. Okay? And so let me ask you a question. If you expected to measure something happening 100 times per second, but you only took 50 samples across that second, do you think that it would be appropriate to measure that thing happening 100 times per second? I hope that the answer, of course, would be no, because you can see here on the right we have a frequency spectrum or a power spectrum density. We're putting our sampling of our signal through a Fourier transform, and we're trying to measure the frequencies that are in our signal. And you can see that we have this spike here. This spike is the measurement, for those unfamiliar with Fourier transforms or frequency spectrum, power spectrum density type stuff. And you can see that we have a nice big spike here, damn near at 0 hertz. And that's problematic, because this is a perfect simulated 1 second long 100 hertz sine wave. And so what is this that we're measuring here? What is this that's here in our measurement? Well, it's fictitious noise. It is noise called aliasing. And it's called aliasing because it is an alias of our actual 100 hertz frequency, but it's not at 100 hertz. It's not measuring 100 hertz because our sampling is inappropriate for being able to actually measure 100 hertz. And so with this, in a moment, when I kick off this animation, you'll see that we're going to increase our sampling. And just watch what happens to our measurement on the right as we start to increase our sampling. So here you can see our sampling is beginning to change. We're taking more and more samples across this 1 second of data, and you can see that our spike, or our measurement for the frequency, is starting to shift and bounce around and move around. The magnitude is also starting to grow as well. Now we're over 100 hertz, and you can see it's still starting to bounce around, but we're measuring less than 50 hertz, and which is problematic, but now it's pushing up, and it's moving closer and closer towards the expected 100 hertz frequency we expect to measure. And as it continues, you can see it's getting much closer and much closer. And now that we're above 200 hertz, you can see we are measuring that 100 hertz frequency, and it's actually completely stopped dead in its track. Our spike is no longer moving. As a matter of fact, the only thing that's happening to it is its amplitude is growing, and that's because now we are appropriately sampling our signal to be able to measure this 100 hertz frequency. And we're going to stop here at 300 hertz. But you could see that we could just keep going, and the magnitude would just keep getting better. We would be at a much greater resolution here. But there's no need for us to really go above, let's say, like 201 hertz based off of the theorem. And so how does this translate to our data? Well, these frequencies in data would represent some type of feature that you might be trying to measure. If you don't sample things appropriately, you're not going to be able to measure that feature. And so in order for you to retain all the information that you care about in a data set or in a signal, you need to sample whatever it is that you're trying to measure or study properly. Whether it is a simulation, an animation, whatever you name it, you're going to have to sample it properly.